Good day, class. You're welcome to another section of our lessons, and I want you to sit back and enjoy the lesson as we continue. So today we are going to be looking at energy level in atoms. That's what we are going to be looking at, energy level in atoms. So when we look at this previously in studies, it is observed that the energy level of an atom is used by the atom in moving around a positively charged nucleus. This is why the energy level starts from the simplest positive charge. We cannot assume that the energy level of every atom is the same, but the book came with the conclusion, which we are going to look at below. From Bohr's atomic theory, we can see that Bohr put forth some model of atom in the year 1915, which will guide us on the energy level in atom. So some of the postulates that Bohr put forth for us are: electrons inside atoms are placed in discrete orbits called stationary orbits. Another of such is that the energy level of these shells can be represented via quantum numbers, where we have n equals to 1, n equals to 2, n equals to 3, and so on and so forth. So he also made mention that electrons can jump to higher levels by absorbing energy and moving to lower energy level by losing or emitting its energy. So electrons jump to higher levels by absorbing energy, and they move to lower energy levels by losing energy. So when they move to higher energy levels, they absorb energy and move to higher energy levels, and when they lose energy, they move to lower energy level. So as long as electron stays in its own stationary, there will be no absorption or emission of energy. So that is the case. So these are some of the postulates of Bohr. So the last we are going to look is that electrons revolve around the nucleus in these stationary orbits only. So you can see that electrons revolve around the nucleus in series. So electrons revolve around the nucleus in series of energy levels. So that is what we have. Electrons revolve around the nucleus in series of energy levels. So now we are going to be looking at hydrogen energy level. Now, hydrogen atom with one electron is considered to have the smallest positive charge. So for hydrogen, the ground state is represented as E0, and E0 is the ground state or the lowest energy level, and it is 13.6 electron volts. So that is the ground state. We have other excited state as E1, E2, E3, E4, and so on and so forth. So other excited states also exist, like E1, E2, E3, E4. They are called discrete energy level from the formation E0, where N1, n equals to 1, 2, 3, 4 is our quantum numbers. So we are going to go into excitation energy. What is excitation energy? Excitation energy is the energy required to take an electron from the ground state to an excited state. That is excitation energy. The energy required to take an electron from ground state, which is E0, to an excited state, maybe E1, E2, E3, E4, or so on and so forth. So that is what we call the excitation energy. So energy required to take an electron from the ground state, which is the E0, to excited state, which is E1, E2, E3, E4, or thereabout. So that is excitation energy. So we are going to look at diagrams of the excitation energy. We have the electron moving from N1. When it moves from N1 to N2, it loses 10.2 electron volts. It gains 10.2 electron volts. So when it absorbs 10.2 electron volts, it moves from N1 to N2. And when it moves from N2 back to N1, it loses 10.2 electron volts. So this one, the electron moves from N1 to N3 by absorbing 12.1 electron volts. So remember we said an electron move from a lower energy level to a higher energy level by absorbing energy, and also moves from a higher energy level back to a lower energy. So it moves from a higher energy level to a lower energy level by losing energy, and moves from a lower energy level to a higher energy level by absorbing energy. So now let's look at an exercise. An element has energy of minus 13.6 electron volts at ground state. If it is excited to the third energy level, which has an energy of minus 1.51 electron volt, determine the excitation energy. Now in this case, we are asked to determine the excitation energy. So the electron has an energy of minus 13.6 electron volt at ground state. If it is excited to the third energy level, which has an energy of minus 1.51 electron volt, determine the excitation energy. So we are going to look at the first energy is minus 13.6 electron volts, and we also have minus 1.51 electron volts. So we are going to look at the difference between these two energy. So that is what is going to give us the excitation energy. So E2 was given up to us as minus 1.51 electron volt, while E1 was given to us, while E0 was given to us as minus 13.6, which is the ground state. That's why we call it the E0, minus 13.6 electron volt. So what did we come up at E2? We subtract E0 to give us 12.09 electron volts. That is what it's going to give to us, electron volts. That's what it's going to give to us. So now let's continue. So now we're going to have also in other way it can be calculated, where we have E0 equals to minus 13.6 electron volt, and E2 is minus 1.51 electron volt. So when you do the subtraction change in E, you're going to have E2 minus E0, which is minus 1.51 electron volt, subtracting this. So the two negatives are going to result in a positive, and the positive will subtract this to give us 12.09 electron volt, as seen below. So this is just a typical illustration of what we have. In that context. So E2 subtracting E0 to give us that. So that is the illustration we have, as we can see above. So you can see how E2 and E0 is the ground state, while E2 is the third energy level. This is the first energy level, which we call the ground state, second energy level, which we call the E1, and third energy level, which we call the E2. So now let's look at energy quantization. What is energy quantization? Energy quantization is the process by which a pack of radiated energy known as photon or quanta is emitted when heat is applied. So a pack of energy known as quanta is emitted when heat is applied. It's called energy quantization. So when quanta is emitted when heat is applied, we call it quantization, energy quantization. So changes E is still the same thing as HF as we know. So process whereby quanta is being emitted when it is applied is called energy quantization. So changes E is AC over lambda, which is what we also know, AC over lambda, or HF, which is what we also know. So a spectrum is defined as the characteristic wavelength or electromagnetic radiation or a portion thereof that is emitted or absorbed by an object of substance, atom, or molecules. So we are going to be looking at spectrum. A spectrum. So we are going to be looking at spectrum. A spectrum is defined as the characteristic wavelength of electromagnetic radiation. The characteristic wavelength of electromagnetic radiations that is emitted or absorbed by an object. So characteristic wavelength of electromagnetic radiation that is emitted or absorbed by an object. So that is what it is. So examples of spectrum include the rainbow. We have the emission colors. We have the rainbow, the emission colors from the sun, and the infrared radiations, the infrared absorption wavelength from the molecules. So we have these as the various examples which are going to illustrate the continuous spectra. The rainbow gives continuous spectra. The emission of colors from the sun is giving us emission spectra, while the infrared absorption of wavelength is giving us absorption spectra. So we have the continuous spectra, which is the rainbow. We have emission spectra, which is emission of colors, and we also have absorption spectra, which is absorption of wavelength from molecules, right? So that is what we have. So these are typical illustration of how they look. We have the emission spectra, we have the continuous spectra. Continuous spectra is rainbow. Emission spectra is also there. Emission of colors and absorption spectra is also a typical example of the absorption of light. Alright, so now we are going to be looking at our second exercise, which is what we are going to be looking at. So they said the ground state of hydrogen may be represented by the energy minus 13.6 electron volt and the first excited state by minus 3.4 electron volt. The scale in which an electron is completely free of the atom is zero energy. Calculate the frequency. Now here we are told to look for the frequency, but not only the frequency, we are also told to look for the wavelength. So here we are told to look for both frequency and wavelength. Got the question very well. The ground state of hydrogen may be represented by minus 13.6, that's E0 is minus 13.6, and excited state, first excited state, E1 is giving us minus 3.4 electron volts. So we are asked to calculate the frequency. So we are told to look for the frequency of the radiated Planck, the frequency, and also the wavelength of the radiation. So these are the two things we are asked to look for: the frequency and the wavelength of the radiation. So let's proceed. Let's see what we have there. So for our solution, we are going to be having E0 according to the question is minus 13.6 electron volt. That is E0. So from our question here, we have E0 as minus 13.6 electron volt, and also we have E2 as minus 3.4 electron volt. That is what we are given to calculate with. So we have E2 and E0. Also, we are going to have a change of energy, which is going to give us E2 minus E0. For us to have the change of energy, we are going to be doing E2 minus E0. So if we do E2 minus E0, what we are going to be having is minus 13 minus 3.4 minus 13.6, which is going to give us 10.2 electron volt. Also, remember that Planck's constant is 6.6 according to the question, times 10 raised to power minus 34, which was given to us as the question to use. 6.6, that was what we were given to use. So we'll stick to that. Alright? So using the formation E equals to HF, we are going to be looking at, because we are told to look for frequency, that's why we're using the formula E equals to HF. So when we do that, our E, remember change in E, which is E1 minus E2 gave us 10.2 electron volt. So that is where our E is, 10.2 electron volt. While H here is the Planck constant and F is the frequency we are asked to calculate. So when we substitute, we have 10.2 times 1.6 times 10 raised to power minus 19, which is going to give us 6.6 times 10 raised to power minus 34 times F, because 1 electron volt is 1.6 times 10 raised to power minus 19. Anytime you see electron volt, you change your electron volt first to joules before you can calculate. You cannot calculate using electron volt because the SI unit of energy is joules. So you have to convert the electron volt first to joules. That is by changing it by multiplying by 1.6 times 10 raised to power minus 19. So we are going to look for frequency in this case. So if we make F the subject formula here, we are going to be having 10.2 times 10 raised to power 10.2. So we'll be having 10.2 times 1.6 times 10 raised to power minus 19 equals to 6.6 times 10 raised to power minus 34. This is 10.2, which is the energy. Then this 1.6 came as a result of electron volt, and H came as a result of Planck constant, 6.6 times 10 raised to power minus 34. Making subject formula the frequency, we are going to be having 10.2 times 1.6 times 10 raised to power minus 19, all divided by 6.6 times 10 raised to power minus 34. So that is what we are going to have in this case. So now if we do that, we are going to be having something like 10.2 times 1.6 times 10 raised to power minus 19 plus 34. When we carry this minus 34 up, we're going to get in positive 34. So final answer is going to give us 2.4615 times 10 raised to power 15 Hertz. Thank you very much. I hope you got that. Okay. So now we are also told to look for the wavelength of this. So not only the frequency, we are also told to look for the wavelength. So for us to get a wavelength, we are going to be using E equals to AC over lambda, or you can also calculate the wavelength using this frequency. But let us see what we want to do. So if we calculate using frequency, wavelength is equals to speed of light divided by frequency, which is going to give us 3 times 10 raised to power 8, or divided by 2.4615 times 10 raised to power 15. 10 raised to power 15. I hope you heard that. So we're going to be looking at our third exercise, exercise 3. We're going to be looking at exercise 3. Exercise 3 say an electron jumps from one energy level to another in an atom radiating 4.5 times 10 raised to power minus 19 joules. If Planck constant is 6.6 times 10 raised to power minus 34 joules. Alright, so we are told to look for the wavelength of the radiation. What is the wavelength of the radiation? Okay, so to get the wavelength of the radiation, this is what we are going to do our solution. We are going to use E equals to AC over lambda because we are told to look for wavelength. So E equals to AC over lambda, right? So where E is given to us as 4.5 times 10 raised to power minus 19 joules, and H is given to us as 6.6 times 10 raised to power minus 34. The speed of light remains 3 times 10 raised to power. So we have speed of light as 3 times 10 raised to power 8 meters per second. So Making lambda the subject formula in this case, we have lambda equals to AC over E. Or peradventure, you can calculate with this formula, and at the end of the day, you make subject formula, or you can also make a subject formula before calculation, whichever way you are good at. You can do that. So we are going to have lambda equals to 6.6 times 10 raised to the power minus 34 times 3 times 10 raised to the power 8. So this is Planck's constant that we are given. We are given Planck's constant 6.6. We are given 3 times 10 raised to the power 8, all divided by energy, which is 4.5 times 10 raised to the power minus 19 joules. So when we do that, we have our final answer as 4.42 times 10 raised to the power minus 26 meters. Hope you enjoyed it. Thank you very much, and have a nice day. Please make sure you subscribe to our channel. Thank you very much.